Hey guys, so last time we were talking about the macromolecules. We know that macromolecules have a large number of atoms bonded together by a very large number of strong covalent bonds. And then we looked at how diamond and silicon dioxide are both similar because they were both macromolecules. They both had a large number of covalent bonds. They both were tetrahedral structures. But then we also saw that how they are different because diamond is pure element carbon. All the carbon atoms were there. And how silicon dioxide was actually a compound because it was a combination of silicon atoms with oxygen atoms, remember? And then we saw the properties of diamond and silicon dioxide which were in common because we saw they both had a very high melting and boiling point because the atoms are strongly bonded by the covalent bonds, and it requires a very large amount of heat energy to break these covalent bonds. It's not that weak intermolecular attraction, it's strong covalent bond. And while we saw they were bonded, so their valence electrons were occupied in covalent bonding. And the valence electrons are now not free anymore, they are not mobile anymore, they are not available anymore to conduct electricity. In today's video, we're going to be looking at a new kind of macromolecule which has some kind of properties similar to diamond and graphite, like I mean diamond and silicon dioxide, but few properties are a little different. So I already named it. It's going to be graphite. So today we're going to be talking about graphite. So let's write graphite over here. We're going to be talking about graphite. So graphite is also a form of carbon. So graphite also has carbons in it, but the issue is that graphite has a little different structure. So I'm trying to draw it over here, and we'll see how the structure is overall similar or different. So that turns out to be something like this. It's gonna be like this over here and over here. So if I were to make my bonds over here, these are my bonds gonna be. Each carbon definitely seems to be bonded to three more carbon atoms. It's six membered ring, but each carbon is bonded to three more carbon atoms. If I can stretch the structure, it might look like this. It goes on, and this would be a continuation of the structure of graphite. It goes like this. I'm making these bonds to show that this structure never stops. It keeps on growing like this. If you look at the structure, you can see that each graphite is making three covalent bonds. Each molecule, each atom of graphite is making three covalent bonds like this over here. If I label them the carbon atoms, and let's identify one over here. For example, I am going to be talking about this particular carbon atom. We can see it makes one bond over here, one over here, one over here. So it is making three covalent bonds. Similarly, for example, this carbon atom also makes three covalent bonds, one over here, one over here, one over here. Similarly, this one over here, one with the right side, one over here. So each carbon is making three covalent bonds rather than four. One thing is really interesting over here, that graphite structure is not only one layer of the hexagon, it is a continuation layer. So it has actually multiple layers like this. It has multiple layers of the carbon atoms like this. So this over here would be my first layer. This would be my first layer which I am making with a light pink highlighter. And over here I would be having some other layer over here. For example, that would be my orange layer. I'm showing the continuation of the layers. So this is layer number 1, layer 1, and this would be over here layer 2. Both have layers of hexagonal rings. Both have their layers of hexagonal rings, hexagonal carbon rings, and these layers are held together by weak intermolecular forces. So the layer has covalent bond. This is the covalent bond over here. This is the covalent bond between the carbon atoms over here, These are the covalent bonds like this between the carbon atoms. But between the layers, there is weak intermolecular forces. Between the layers, there is weak intermolecular force, aka IMF. So we know two things about it, that it's gonna be having a very high melting and boiling point. For the same reason, graphite has a very high melting point slash boiling point for the same reason as diamond and graphite, that large number of strong covalent bonds, right? Large number of strong covalent bonds, and they cannot be broken easily. I mean, I'm not talking about the IMF right now, I'm talking about within the layer. Within the layer, there's a large number of covalent bonds, and obviously, we need very high heat energy is needed to break these bonds and to make the carbon atoms go separate ways, and it is something not really easy. So we have a large number of strong covalent bonds. It cannot be broken that easily. When we talk about the layers, we know that there are layers, multiple layers over here, and these layers can slide over each other. So actually, these layers have a capacity to slide over each other without breaking apart. If I just make this structure a little smaller over here, for example, this is my layer number 1, and let's suppose this would be my layer number 2. I'll make the small pattern over here again. For example, this is our layer number 1 with all the hexagons, and this would be layer number 2 with other hexagons of the other layers, like this. They have weak intermolecular forces between them. They have weak intermolecular forces. So they kind of slide over each other. They can very easily, let's move it, they can slide over each other like this. And that is why the layers are slippery. So what happens is that graphite is slippery because the layers can slide over each other. They have weak intermolecular forces. The layers have weak intermolecular forces between them, and they slide over each other. Remember, metallic lattice also had layers. Similarly, graphite structure also has layers. So, and they slide over each other, right? I write just like a metallic lattice, just like a metallic lattice. Now the third thing is going to be that each carbon atom has made only 3 covalent bonds, and that means each carbon atom has one mobile electron over here. Each carbon atom has a mobile electron, and their electrons can be used to conduct electricity. So when we talk about the mobile electrons, they can be used to conduct electricity. They can flow. So these are the mobile electrons. Mobile electron. So each carbon atom makes only 3 covalent bonds, and that is why the 4th unbonded electron can be used to conduct electricity. Graphite conducts electricity, unlike diamond and silica, because they both did not conduct electricity, but graphite does. So the reason is each carbon atom makes 3 bonds. The 4th unbonded electron is mobile and can flow. The electron is going to flow to conduct electricity. So it's got something similar with diamond and silica, something different. What's same? So the very high melting and boiling point thingy is same, right? Because They both also had a large number of covalent bonds which required high heat to be required to break the bonds and to make the structure molten. Graphite is very slippery. Diamond wasn't slippery. Diamond did not have any layers. So we should recall over here that diamond has no layers, rather that was tetrahedral. Diamond was a tetrahedral structure, but graphite has layers. It's not tetrahedral, rather it has hexagonal rings which are arranged in layers. And then we saw that graphite conducts electricity, but diamond did not conduct electricity. So by the end of this video, we know how diamond and silicon dioxide and obviously graphite are similar to each other and how they are different from each other. So in the next video, we're going to be solving some past papers of these chapters. So guys, see you then.